So the factories or the industrial load consumes the apparent power. But do you know, out of the total apparent power consumed by your factory, how much is the active power and how much is the reactive power? Like your factory is consuming the power that actually does some sort of work like the active power, or your factory is consuming more reactive power which is not doing any sort of work, useful work, I can say. Like, do you have any idea, or you don't have any idea about why your factory's electricity bill is going up and up every month? The reason could be the poor power factor or low power factor. Well, power factor is certainly very, very important and very crucial term for both the industries and also for the distribution utilities. Because if you maintain a bad power factor or poor power factor, the utilities will charge the penalties on that. Now, why it is like that? It's your factory, it's your load. Why the utility is concerned about it, right? You will understand that by the end of this video why utilities are concerned about the power factor and why you should also be concerned about the power factor. By the end of this video, the concept of power factor will be crystal clear to you. You will be even explain the concepts to others. Now, before we go and directly understand what is power factor, it is important for us to understand few basic concepts, and those are like the active power, reactive power, and apparent power. It's very, very crucial that you understand these three power if you want to know and understand power factor very clearly. So let us start with that. First, let us start with a very simple circuit that you can see on your screen. We have a 50 Hertz supply and we have a load which is purely resistive load. And you can see we have connected an ammeter and voltmeter to measure the voltage and current. Now I'm going to start this simulation and show you the waveforms for the voltage and current. Now the simulation has started, and on top you can see the waveforms. Now by looking at this waveform, we can say that both the voltage and current are in phase with each other. What does that mean? Let us understand. Now here is the waveform of the purely resistive load that we had. These waveforms are perfectly in sync with each other. They are called as in phase with each other. What does that mean? It means that both the waveform reaches their peak value at the same time. So it could be the positive peak or it could be even the negative peak at the same time, exact same time. And then they also reach their zero value at the same time only. When this is true, then we can say voltage and current are perfectly in phase with each other. They are perfectly in sync with each other, right? This is, you will see in purely resistive circuit. The behavior of voltage and current is different in the inductive and capacitive circuit that we will see in few minutes. Now, if you further analyze this waveform very clearly and we try to calculate the power that is there in this resistive load, then what we can notice is the power is always on the positive side. What is that? Let me explain. So first, to understand that, we will calculate the instantaneous power. Now, what do we mean by instantaneous power? It is a simple concept which states that if you want to calculate the power at this particular instant where both voltage and current are at its peak, then it's called as the instantaneous power. So if you can take any instant on this waveform and calculate the power, you'll get the instantaneous power at that particular point. So in this example, I'll consider this peak point here. Now in this point, you can see both voltage and current is positive. And power is what? Power is P is equals to voltage multiplied by current. So when we multiply voltage and current here, we will get a positive power, right? The power that is on the positive side. Similarly, maybe I'll take the negative peak now. Now both the values are negative here. So negative multiplied by negative will give us a positive value, positive output. And you take any single instant on this waveform anywhere, you will always get the resultant power as the positive power, right? And this is what we refer to as the active power. The characteristics of active power is very clear. They are always positive side. So they don't go on to the negative side of the graph. They will always stay on the positive side. And this is the power that is being used to perform some sort of useful activities. This is very important. If you are consuming this and only this, then you are at the right path. But if out of the total power, if active power is very limited, then there is a problem, right? So active power is very, very important. What is the main characteristics of that? It stays in the positive side always, no matter what. If it is not positive, if it is going to the negative side, it's no more the active power. What is that? That we will understand in the next example. But the simple example of this could be the lighting loads that we have. So for example, if your factory is having only the lights and you 100% know that it's the power that you are going to consume is the active power or the real power, and you can clearly state that the rating is 400 watts or something like that, because you know it's active power only. Clear? So that is the purely resistive load. Now things starts getting interesting when we insert inductor in the system. Let us have a look at that. So here is the second case where we have inductive circuit. So we'll consider it as purely inductive. Now here you can see a small amount of resistance, but that you can ignore and you can consider it as the purely inductive circuit. It is exactly the same that of the last one what we discussed. I've just added inductor into that. Now I'm going to run this simulation and show you the waveforms that you will see. Now I have started the simulation and you can see on top the waveforms are started. And you can clearly notice that the waveforms of the resistive circuit and the waveforms of the inductive circuit is very different. They are no more in phase with each other. So what is happening on these waveforms? Let us understand that. So this is the typical waveform that you will see in the purely inductive load. Now please note I am talking about purely inductive load. If there are impurities, if there are resistance in the system, the waveforms will be different. So this is particular example of purely inductive load. Now here, if you see, the voltage and current are no more in sync with each other. They are different. So they are reaching their peak values at different times. So here the voltage has head start. So voltage is starting early because the very nature of inductor to store the current. So voltage has a head start. So, and that's why we say in inductive circuit, voltage lead the current by 90 degree, or the current lags behind the voltage by 90 degrees. And that's why that's the reason why the peak values of each waveform differs from the another one. So here is the 0 for current, but the 0 for voltage is here. So it's no more in the sync. So they are out of phase by 90 degrees. And this creates problem. How? That you will understand when we calculate the power. Now imagine we will calculate the instantaneous power like we did in the resistive circuit. So I'll take this 2 points as a reference. So on this first point, you can see the voltage and current both are positive. So no problem here. We will get positive power because positive multiplied by positive will give us positive output. But in the second scenario, one value is positive, okay, no problem, but the another value is negative. And when you multiply positive with negative, the resultant is the negative value. And that's what you see. What does this negative power mean? Well, in simple terms, it's the power that is, getting back towards the generator. So positive means it is getting consumed and negative means the load is sending it back towards the generator. And if you notice in purely inductive, or for that matter also the purely capacitive circuit, the power, the positive side and the negative side will be identical. So they will cancel out each other and the total power consumed by the circuit will be 0. Right? What does that mean? It means that the power will go back and forth without doing any useful work. Right? So for example, useful work, you can consider generation of heat, generation of light. That is something we call it as useful. But this power that is going positive and negative back and forth does nothing. It will not generate heat. It will not generate light. So it's just back and forth that is going. And this power is called reactive power. You will find this reactive power in purely inductive and capacitive circuit. In capacitive, it will be the opposite, where the current will have head start and the voltage will lag behind the current by 90 degrees because of the very nature of the capacitors. If you are interested into that, learning about more basics of AC circuits, I have a dedicated playlist. I'll give link for it down in the description. So this power is the reactive power. The example of inductive load, you can consider the induction motor, which is very widely used in the industrial application. But this purely inductive, purely resistive is, I can say, not very practical. What practical is, you will understand in the next scenario. So here is the third scenario, which is the most practical scenario, and you will find such type of circuits in the actual life. So here we have the same circuit as that what we saw previously, but here the load is combination of resistance and also the inductance. And this is the very practical example you will see in the factories or in any sort of load that you take. It's the mix. Now I'm going to start this simulation to show you the waveforms of this. So here you can see the waveform has started, and it's very different than that of the purely inductive load that we discussed. The voltage and current are still out of phase, but it's not perfect 90 degrees. It may be higher, it may be lower, depending on the combination of resistance and inductance that you have in the system. So let's analyze this waveform to understand what is the power scenario in this circuit. So now this is the waveform of the practical load that we discussed, where we have the combination of resistance and inductance. They are out of phase, but it's not 90 degree. And if you calculate the power, so for example, if I calculate power here, both values are positive, it's gonna give me the positive power, no problem. But at this instant, here it's the positive side, one value, another value is negative. So it's gonna give me the negative output. But the problem with this type of load is that you will see the positive power is more compared to the negative power. So definitely they will not cancel out each other. There will be some sort of power remaining that will still be utilized by the circuit. And what element is using that power? Of course, the resistance, because inductor ideally will not consume any sort of power. So this is a problem. You cannot call it this power as the active power because it's not on the positive side. So active power is out of the question. Reactive power, can you calculate this? No. Why? Because the positive and negative peaks are not identical. So this is not even the reactive power. So this is something else. This is the combination of active power and reactive power. And that's what we call as the apparent power. And this is what your factory consumes, because your factory will not have only the lightings, or it will not have only the induction motors. It will have both, right? So your factory is going to consume the apparent power. And absolutely, just by looking at the load, you cannot inform that out of that apparent power, how much is the active power and how much is the reactive power. You cannot tell that, right? So to understand that also, let's take one simple example and we'll understand what is the relation between apparent power and active power. So here is again the practical example of one load. We have 230 volt AC supply connected to a load which is the combination of resistance and inductance. So we have 60 ohms as resistance and 160 millihenry as the inductor. So this could be, let's say, a factory. And in that factory, we have lights, we have induction motors, we have furnaces and different types of load. So this equivalent circuit represents a factory, just for our understanding purpose. Now, this load, if you want to calculate the current, first we need to calculate the opposition that is being offered to the current. Now, it's a combination of resistance and also inductance. So we cannot take any of this value for calculation of current. What we have to have is impedance. Now, impedance is the term used in AC circuit, which tells that it's the combination of all sort of opposition. We have resistance, we have inductance. So we'll take that, we'll calculate the impedance, and so the total impedance is 78.25 ohms in this circuit. And with the help of impedance, we can calculate the current, and that is coming around 2.93 ampere or 2.94 amperes. Clear? So that is the current our factory is currently consuming. Now with this, we can also calculate the different types of power that is consumed by our factory or our load that you see here. So active power I square R, that is 515 watts. Reactive power I square XL, which is 431 VAR, volt ampere reactive. Reactive power will be taken by inductor, active power will be taken by resistance. And the combination of all this is what we refer to as the apparent power, which is given by I square times impedance. And that is 670 volt ampere. Clear? Now, if you have the apparent power, for example, 671 volt ampere reactive, you need to know what is the percentage or what is the amount of active power in this apparent power. How do you know that? Well, you can know that by simply dividing the active power by apparent power. So if you do that, you'll get as 0.76. You can say, let's say 76% of the power, total power that I have is active power, and balance is reactive power. And this ratio of active power and the apparent power is what we refer to as the power factor. Power factor tells you out of the total total apparent power that you are consuming, how much is the active power and how much is the reactive power. And here in this case, it is given, the power factor is 0.7. Now, please remember, power factor is unitless quantity. So it's not like a percentage or ohms or amperes. No, it's unitless quantity. We say 0.7, 0.8, 0.9. It means that out of here, 671 volt ampere, out of that 76% of power is my active power and balance is my reactive power. So actually, ideally you should be consuming, let's say 515 watts, but you are consuming 671 volt ampere reactive. And for this, the utility will penalize you. Why is that? We'll understand it in a few minutes. Now we can relate all these three powers using a simple triangle. It's called as the power triangle. So at the bottom, we show the active power, which is 515 watts in our example. This line indicates the apparent power, which is 671 volt ampere. The angle between these two, you can calculate with the help of the power factor cosine inverse you can take, and you'll get the angle of that. And this ratio or this angle is what we refer to as the power factor. A lot of people will say power factor is the angle between voltage and current. No, that's not the correct definition. You have to say the ratio of active power and the apparent power. So this is the apparent power, and this line, the straight line, indicates the reactive power taken by the circuit, which is 431 VAR. Now, if the reactive power increases in your circuit, in your factory, this angle will increase and the apparent power taken by this factory will also increase, right? So you still need 515 watts, but because the reactive power has gone up, you are actually consuming more power from the utility, right? Now you'll be able to connect the dots. Why utility is concerned about the power factor. So if the reactive power goes up, the power factor will go down, it will become poorer, and you will consume more power than what you need. If that is true, the opposite will also be true. If you reduce the reactive power, the power factor should improve. Let's see that. So this is our first scenario where the power factor is 0.7 and the current taken by our circuit is 2.94 ampere. Now here, let's say we reduce the reactive power by 50%, which is now 231 VAR. You will see the apparent power has also gone down. It is now 564 volt ampere. Earlier it was 671. And the angle between active power and reactive power has also reduced. And the power factor is now 0.9, which is far better. And you can see there is also improvement in the current. Current has gone down. Now here in this example, the difference is not big, but when we talk about huge reactive power, huge factories, huge load, the difference in current is significant. This is also one of the major advantage why you should focus on reducing or improving the power factor. Now you can see the current has gone down, but you're still supplying the same amount of power. So if this is true, in a scenario where your apparent power becomes equal to your active power, in that case, you can say your power factor is perfect, your power factor is unity. But those are the ideal scenarios and it's not possible practically. And that's why utility promotes you to maintain the power factor to zero point 0.9 or 0.95, the best that you can do. Now the question is, why utility is behind you? Because it's your factory, it's your load that consuming the power, you're paying the bill, but why utility is charging more if you consume more power? Well, the reason is you actually need 515 watts, but you are consuming 671 VA. So you need X power, but you are consuming X plus Y. And that Y is doing nothing. No useful work is being done. But that is putting additional load on the utility. And utility, because of that, cannot add another consumer or maybe supply the power where it needed the most. And what is the solution to that? Well, the solution is you increase the generating capacity, you add more transmission towers, you add more distribution network. But that's not the practical solution because it's very costly matter and you cannot do that. The another solution is we'll limit the utilization of reactive power in the consumer premises. We prioritize improving the power factor. And that's why utility will penalize you if your power factor is poor, and they will also give you incentives if you maintain a good amount of power factor. And that's why utilities are also concerned about the power factor. And ideally, you should, if you have a factory, you should also be concerned about maintaining good amount of power factor. Now, the theory is pretty simple. How do you improve the power factor? Of course, what is causing the power factor? The reactive power. It's mostly the inductive reactance that is there in the system. So if reactive power is dropping the power factor of the system, if you add the equal and opposite amount of reactive power in the system, you should be doing good, right? Now, if you want me to make a dedicated video where I can talk about how to improve this power factor, then comment power factor in the comment section below. If I get enough comment, definitely I'll also be making a video in which I'll explain how you can improve the power factor. All right, so now let us summarize this video here. So what is power factor? Power factor is the ratio between the active power and apparent power. That is nothing but the power factor. Now, power factor indicates the amount of active power the system is consuming. So when we say power factor is 0.7, that means 70% of the power that you are consuming, total power, is active power, and balance 30% is the reactive power. Power factor is unitless quantity. We discussed about that. So when we have a purely resistive circuit, the power factor would be unity or the highest one, as the reactive power is 0 in that case, and the apparent power is almost equal to that of the active power. Opposite to that, in case of purely inductive or capacitive circuit, the power factor would be 0. As the active power is 0, the apparent power is equal to the reactive power. Clear? So I hope the concept of power factor is clear to you and this video was helpful. If it was helpful, then do like this video and do share it with the people you think might be interested in knowing. So thank you so much for watching, guys. I'll see you in my next one. But till then, keep watching, keep learning.